Hello, my name is Chris Evans and I'm from Physical Sciences Incorporated. Within this presentation, we will show you our work developing photonic integrated circuits for compact atomic Raman devices, or PICARD. This is part of a Phase 2 SBIR effort for Navy SSP. Physical Sciences Incorporated, or PSI, is a 50-plus-year-old company with over 275 employees. We are an applied R&D company that focuses on technology transition across a wide range of disciplines for both our government and industrial customers. Our expertise includes underwater sensors, integrated photonics, and optical communications. We have developed products for a variety of applications, including ISR systems, laser-based sensors such as the handheld methane sensor shown on the right, radiation sensors mounted on highway gantries, as shown on the bottom left, that monitor the transport of radioactive materials, RF and optical components, as well as tactical systems including ruggedized drones, as shown on the lower right. For every dollar of Phase 2 SBIR investment, PSI has secured nearly 3 times that amount in Phase 3 funding. Inertial navigation is a critical capability for many modern defense systems, particularly in contested and GPS-denied environments. These units use a series of sensors, such as accelerometers and gyroscopes, to measure the forces on a moving platform to calculate and update its position and orientation over time. Traditionally, mechanical accelerometers and gyroscopes, such as the Pendulous Integrating Gyroscopic Accelerometer, or PIGA, have outperformed other technologies, but suffer from complex assemblies and low mean time between failure rates due to their mechanical nature. Recently, quantum inertial measurements have been shown to provide the sensitivity and accuracy required for high-performance inertial navigation applications. These systems use atoms within vapor cells as test masses and read out the acceleration data by probing the atomic vapor with a sequence of laser pulses at very precise wavelengths. In laboratory demonstrations, the required laser system consists of a series of frequency and phase-locked lasers, which often takes up an entire optical table. Even when miniaturized and packaged, these laser systems dominate the size, weight, and power, or SWaP, of the sensor, which greatly exceeds SWaP requirements for many deployed systems. Furthermore, these free space and fiber component systems can be susceptible to mechanical vibration, further limiting deployment. In order to realize a deployable quantum sensor, we need to reduce the size and complexity of the laser support system. PSI's Photonic Integrated Circuits for Atomic Raman Devices, or PICARD, uses a photonic integrated circuit to modulate and route light on a compact and highly mass-producible chip to generate pairs of phase-coherent optical frequencies. Compared to phase-locking lasers, which requires feedback loops, our single sideband modulator generates a second optical frequency directly from an input optical frequency based on a user-defined RF input. Our phase-coherent approach is therefore more stable, robust, and frequency agile than locked laser approaches. While this approach has also been demonstrated at telecommunications wavelengths, our approach works at native atomic wavelengths and at relevant power levels for atomic sensors. In the near term, we are focused on incorporating our PICARD technology as a component within an atomic sensor, while our long-term vision is to create a complete optical bench on a chip. Our approach has 3 key innovations. First, we use the thin-film lithium niobate, or TFLN, material platform. TFLN is highly transparent at visible and near-infrared wavelengths. TFLN can also handle the high optical powers necessary for atomic sensors. In addition, this technology can work at a variety of native atomic wavelengths, such as 780 nanometers for rubidium and 852 nanometers for cesium, simply by changing the waveguide's geometry. Second, we use an IQ modulator architecture configured as a single sideband modulator, which generates phase-coherent optical frequencies without generating parasitic frequencies that can disrupt the atom's quantum state. These cascaded electro-optic modulators are high-speed and require very low RF drive power. Lastly, we are developing high extinction ratio ring resonator modulators to act as on-chip optical shutters, which are needed to extinguish the light during sensor readout. Within the current Phase 2 program, we have completed 2 generations of chips, having demonstrated single sideband modulation in the first generation. Our latest chips include advanced phase trimmers to improve the suppression of the unwanted sideband, low-loss fiber-to-chip couplers for packaging, as well as on-chip shutters with thermo-optic actuators. We are currently developing prototype Picard modulators for delivery at the end of Phase 2. Our technology has several key features. First, our single sideband modulator approach replaces locked lasers, resulting in a robust and agile frequency tuning method that is simpler, is very low swap, and is electronically controlled to be easily adapted to different measurement types. By operating at native atomic wavelengths, we avoid frequency doubling, which both increases the swap and leads to parasitic frequency generation. And thus our approach naturally leads to a lower swap, higher quality sensor that is easier to implement. In addition, our approach can handle high optical powers, avoiding post-modulator amplification. Our high extinction ratio optical shutters can also be used as modulators to reduce system complexity. Lastly, we are using a wafer-scale fabrication method, resulting in highly manufacturable chips that are low cost at scale. Furthermore, these chips can have more optical functions per chip to reduce the number of components within the system to further reduce swap. To support next-generation inertial navigation systems, we will create fully packaged Picard devices that will include our high-speed single sideband modulators controlled by an RF input, high extinction ratio shutters controlled by a digital input, and a control module to stabilize the system, making it easy to integrate into existing sensors. This technological approach is very general and can be applied to a number of different applications. How can this technology simplify the laser system for your application? To commercialize Picard products, we see two pathways. First, a basic fully packaged Picard module will contain one single sideband modulator to produce pairs of phase-coherent frequencies. The modules will be paired with control electronics to operate the single sideband modulator and shutter. Expected initial customers will include Navy SSP, DoD primes, system integrators, and quantum sensing companies. The end user will supply the lasers and the RF control. This approach most quickly transitions PSI's technology to develop near-term atomic sensors. Second, we will create advanced multi-frequency Picard modules. These modules will contain multiple single sideband sections along with optical shutters developed for specific sensor architectures. Expected customers will include Navy SSP, DoD primes, system integrators, and quantum sensing companies. This approach will reduce the cost of specific sensor products for widespread deployment. Our anticipated end users include Navy SSP, NAVC, MDA, the Air Force and Space Force, in addition to quantum sensing and computing companies. In summary, PSI is developing advanced modulator technology for generating phase-coherent optical frequencies for atomic-based measurements and sensor systems. Our technology reduces a complex locked laser system to a series of programmable, user-defined pulse sequences leveraging agile frequency shifting. While this technology is targeting atomic sensors for the Navy, similar atom-based measurements are possible for other quantum sensing and computing applications. Come chat with us to learn how Picard can simplify your laser system implementation.